All right, how many people do we have? All right, last time we worked out the following formula for the effective focal length of a pair of lenses. We said that if we've got two lenses separated by a distance d, then 1 over the effective focal length was 1 over FA plus 1 over FB minus d over FA FB. All right. And we work that out by saying that, all right, these rays of light will come to a focus here, a distance FA to the right, and then they will keep on diverging. And those rays will subsequently, come to a focus here at a distance y equals F effective tan theta. And so we can define F effective via this. We could do all the back and forth to figure out where does this image form, and then where does the image of this point in turn form. And this is going to be a distance FA tan theta. And this will be at some other height. And we worked out the magnification and we got all that. Any questions so far?
Okay, Sarah, so do you have any questions?
All right, well, people combine lenses for a lot of reasons. One of the reasons why people combine lenses is to make telescopes, which we'll talk about today. Another reason is to reduce aberrations, which you're going to see examples of on assignments 4 and 5 and 6. And let's talk about telescopes. So first of all, what happens if the distance between the lenses were 0, and let's assume FA and FB are both positive. That's not always the case, but we'll assume it is here. If the distance between the lenses were 0, then we would just have 1 over F effective equals 1 over FA plus 1 over FB. Will the combined focal length of this system be smaller than FA and FB or larger than FA and FB or somewhere in between? I want you to vote in the chat. Think about the formula and then think about what happens. And if we think about the formula and then put your answer in the chat.
Could you repeat the question one more time, Dr. Small?
Is the effective focal length smaller than either of those? Larger than either of those? Or is it in between? So if we say that FA is the shorter focal length for the sake of argument, what's going to happen when we combine the lenses? Is the effective focal length going to be between the two, less than either of them, or larger than either of them? Put your answer in the chat. Greater, less, or in between? Each of the 3 possibilities now has 1 vote. Okay, now we're getting some divergence here. Let's see how it shakes out. Well, let's see here. 1 over FA plus 1 over FB is greater than 1 over FA. It's also greater than 1 over FB. So this is larger. The inverse of the effective focal length is larger than either of the individual inverses. But if the inverse is larger, that means that the actual value is smaller because inverting something flips everything around. So the focal length is shorter. All right, now, what happens if I start subtracting off D over FA, FB, meaning that instead of having the lenses right up against each other, now I start moving them apart. And so I start subtracting off this thing. Now what happens? As I move them farther apart, does that increase or decrease the effective focal length? Increase or decrease? Vote in the chat. Okay, it looks like most people have weighed in. Well, let's see here. 1 over F effective definitely drops, but that means that F effective rises as we move them apart. Remember, if a number gets smaller, 1 over that number gets bigger and vice versa. If a number gets bigger, 1 over that number gets smaller. Okay, so eventually, let's say that D equals FA plus FB. In that case, something very special happens. In that case, we've got 1 over F effective equals 1 over FA plus 1 over FB plus FA plus FB over FA, FB. Let's see here, the first term, it's going to be FA over FA, FB. And the second term is going to be FB over, oh, and that should have been a minus sign there, excuse me. FA's cancel there, and I'm left with 1 over FB. FB's cancel here, and I'm left with 1 over FA. So I get 1 over FA plus 1 over FB minus 1 over FA minus 1 over FB. Ooh, looks like everything tweeted terribly and got canceled, and we're left with 0. Now, you may be thinking at this point that a system with 0 focal length is, with 0 inverse focal length, that is useless. Far from it. Let me explain. Actually, I'll just do one. So we've got our 2 lenses, and we'll say that the first one has a long focal length. So these rays come in and they're making an angle theta, and they all come to a focus here. All right, now this height is y equals FA tan theta, right? Over here, they're all making angle theta. They form an image FA away. Okay. Now what? What will these rays do? They're gonna keep spreading out and hit the second lens. What are they gonna do when they hit that second lens? What do a bunch of rays that start off one focal length away from a lens do when they hit that lens?
They go parallel to infinity.
Parallel to infinity? Do you mean they go to infinity parallel to each other?
Parallel to each other.
Yeah,
Sorry.
right? Because whatever light can do in one direction, light can do in the other direction. So if they start off going parallel to each other from infinity, they're going to go to the focal plane, not the focal point. Okay, this is not the focal point here. But it is in the focal plane. It's in the same plane as the focal point. All right. So if rays going parallel to each other will go to a point in the focal plane, and the point that they go to is at an off-axis distance f tan theta, then the reverse must also happen. Rays that start off in the focal at a point in the focal plane must all go parallel to each other on the other side. All right, if they all go parallel to each other on the other side, how are we going to calculate that angle? We'll call this theta 1, the angle that it's coming in at. Theta 2, the angle that it comes out at. How are we going to calculate theta 2? Someone.
I'm sorry, could you repeat that?
How are we going to calculate theta 2? All right, we know that they started off at an off-axis point in the focal plane of the second lens. And they're gonna go to that lens, and then when they travel through the lens, they're gonna go parallel to each other. How do we figure out what that angle would be?
Can we do 180 minus theta 1?
Why would you guess that?
Because the lines are parallel, and then from congruent angles, they should be equal.
Oh, well, these two lines are certainly parallel to each other. But who said anything about it being like these lines? I mean, these lines are going up and to the right. These are going down and to the right.
Oh.
So a 180 flip certainly wouldn't be in the cards. 180 flip would just completely reverse. You probably mean to guess a 90-degree flip. But does that second lens have any idea what they were doing before hitting the first lens? Yeah, that second lens doesn't have any idea what they were doing before hitting the first lens. Think about it just like this. I've got a lens. All right, let's think about the forward process again, and then we'll try to figure out the reverse process. If I had, get that out of here. If I had a bunch of rays coming in like this, they will all go to a point one focal length away. Right now, if I somehow put a very cleverly arranged system of curved mirrors here, so that every ray is going to get back reflected. I basically put a sphere centered on that point. If I just back reflected every ray, let's see, before y equals f tan theta, f tan theta. They reach a point off axis that's f tan theta from the axis. I could just as easily write that as tan theta equals y over f. And then when they turn around, they could go, if I put some reflector there, they could go back through the lens, and then they would all be traveling at an angle given by this. These are the same equation, really. They're written out differently, but they're the same relationship. So if I've got a point source, I've got a whole bunch of rays coming from a single point, one focal length away from the lens, and somewhere off axis, the angle that they make once they've traveled through the lens is given by tan theta equals y over f. So, any questions on that case? Anyone? Going once, going twice. Okay, now, can someone tell me what must happen in the case above? There are all these rays, they've come together at a point in the focal plane. There's nothing there to stop them from traveling, so they don't stop traveling. I'm drawing them in a different color just to emphasize it's the next stage of their journey. What are they going to do when they hit that lens? They're going to go parallel to each other. And how are we going to find the angle? Someone asked, how does the theta on the left work for the theta on the right? I don't know. The theta on the left doesn't receive a paycheck from the theta on the right. And yes, that was a flip comment, but the point is that the lens on the right has no idea about the theta on the left. The lens on the right has no idea that the rays were originally parallel to each other and then they hit a lens. All it knows is that there are a whole bunch of rays coming from a point, a distance y off axis. Okay, that's all it knows. It doesn't know that these rays come from this lens. They didn't have to come from a lens. There's any number of ways that all those rays could have gotten to that point. Doesn't matter. The second lens could not care less. All right. It's like Officer Krupke, who does not care one bit about the kids' past in West Side Story. Okay. All Officer Krupke cares about is what they're doing at that moment. He doesn't care about their past. They sing about their past. He doesn't care. The lens is Officer Krupke, doesn't know those rays past. All it knows is that they come from a point they come from a point, a distance y off axis. So what is theta 2? Please don't make this hard.
Since it's in the focal plane, can you just do y equals fb tangent theta 2?
Yes. Leona, what were you going to say?
If we're looking for an angle, I just was also maybe going to suggest Snell's law, but maybe that's easier.
Snell's law, well, in some sense, of course, Snell's law applies. Each point on the lens where the rays hit, Snell's law is obeyed. But these rays are hitting many different points on the lens at many different angles. And then somehow they're all going at the same angle once they've exited the system.
Right.
But remember, whatever light can do in one direction, light can do in the other. So if rays hitting the lens come together in the focal plane, a distance f tan theta, y equals f tan theta away, in the reverse direction, tan theta is y over f. So I conclude that y equals fb tan theta 2. Of course, y is also fa tan theta 1. So tan theta 2 over tan theta 1 equals FA over FB. Questions? Somebody must have a question.
Is it a coincidence that looks like Snell's law?
How does it look like Snell's law?
Snell's law is n sine theta or n sine theta 2 or 1 is equal to n sine theta 2.
And
So
we don't
kinda
have any
similar.
n's in here, and we don't have any signs in here. So, I mean,
Okay.
it's something multiplied by a trig function equals something else multiplied by a trig function. But there are things like that throughout optics. There's the Abbe sign condition, which is n1, y1, sine theta 1 in a different situation. There's Herschel's condition, which is z1, n1, I think it's sine squared theta 1. You know what? I'm just going to look it up. I'm just going to consult the Bible. The Bible being Born and Wolf Principles of Optics. This book was written originally in the 50s, before the invention of the laser. Everything in here is still 100% correct and applicable. All right, Herschel condition. What was I trying to say? I was trying to say that there are a whole bunch of places in optics where you get something multiplied by a,
Dr.
Yeah.
Small,
yeah.
I learned about that book from an old professor of mine. Do you think it'd be any useful at an undergraduate level? Because it's from what I understand, a higher level text.
This book, I was completely wrong about the, so you can rewrite it as n1, y1, sine theta 1 over 2 equals n2, y2, sine theta 2 over 2. Okay, would this book be useful for an undergraduate? The answer is that this is not a book you sit down and read cover to cover. This book is useful for anyone and no one. This is a book that you sit down and read a tidbit of it because you're curious about something. And then you realize that you would probably have to actually go back and read the beginning of the chapter in order to understand it. This is a book that you study in bits and pieces here and there over many years. So there is absolutely nothing wrong with starting on this book as an undergraduate, but you should be under no illusion that you're going to understand the whole thing from cover to cover, or even from the first to last page of a single chapter as an undergrad. The truth is that I only understand a section of this book after I really need to, after I've got some problem in my head that I've thought about and I realize I need to go to the next level of rigor. And once I've already chewed on the problem a little bit, and so some of the contours and ideas of the problem are truly clear in my head, then I'm able to actually really get the whole point of everything that they were saying in here. So sure, go ahead and get this book and start studying it. Don't ever have it, and don't feel bad that you, God, I hate to sound like one of those reassuring, sensitive New Age professors, but don't feel bad that you're not going to understand the whole thing. Don't be haughty and think you will understand the whole thing. It's just one of those things that you understand in bits and pieces as you need it. And what else was I going to say? There was one other thing I was going to say. Yeah, so about Bibles of physics, there are a bunch of books that are sort of the classic in their field, and so they get called the Bible of optics or the Bible of whatever. The other Bible that everyone talks about is Numerical Recipes. The original version was written in Fortran. This is basically the gospel. We know it's the gospel because it has 4 authors and was originally written in an archaic language, much like the gospels. Now, I heard someone say in the chat that if it was written in the 50s, it's like the Old Testament. The Old Testament is slightly older than the 1950s. The Old Testament goes back to the Middle East, to the people who actually invented reading and writing. But anyway. Okay. So where were we? So that all of this digression on equations from famous books was to say that just because you've got something multiplied by a trig function equals something else, that doesn't mean that there's an immediate connection to Snell's law. I mean, it's optics, so whatever physical implications that carries must be consistent with rays traveling via Snell's law, but I would not say that it is Snell's law.
Dr. Small, I had a question about y equals FB tan theta 2.
Okay.
In this case, the rays are coming out parallel. What are y equals 0? Because they don't converge, and there's no I guess y.
No, the y on one side equals tan theta on the other side. In this scenario over here, okay, you see all of these rays on the left side are at different off-axis distances. Even different parts of the ray are at different off-axis distances. I mean, here's a y, here's another y, here's another y. So there's a bunch of different y's on that one ray. Likewise on this one. Down here, the y's are negative. Up here, the y's are positive. Okay? All of these rays on the left side have different y's. All of these rays on the right side are making different thetas. But in the focal plane, they are all the same distance from the axis. Does that clear things up?
Yes, thank you very much.
Okay. By the way, you said if you ever become an elected official, you're going to swear your oath of office on Born and Wolf. No, you should. Every great physicist should swear their oath of office on the Feynman lectures. But anyway, or Newton's Principia.
So are spherical aberrations worse in, I mean, maybe that's obvious, maybe not, that's why I'm asking. Is there spherical aberrations worse when you have multi-lens systems like this?
A well-designed multi-lens system actually compensates for spherical aberration.
Gotcha.
All right, if you choose the right lenses and the right combination, you can actually partially compensate for spherical aberration. Okay, so the whole idea of this system is that it takes rays that were making small angles with the axis and turns them into rays that are making big angles with the axis. Why do we want that? Well, let's think about what we would really use a telescope for. You use a telescope to, collect light from distant objects. Now, the thing about distant objects is that nobody talks about a star in the sky by saying the star is this many meters or this many kilometers or even this many light years off axis, okay? That doesn't, because for starters, everybody would have a different optic axis pointing in a different direction. What they say is this star is this many degrees above the horizon or this many degrees away from whatever reference point in the sky. Okay, that's what people talk about. That's what matters. How many degrees away from some reference point in the sky is this star? That determines what angle, what direction you're going to point your telescope in. Now, if two stars are right next to each other, then they are going to be hard to tell apart from each other. So let's say we've got, I will draw these stars, these rays in different colors. We've got a bunch of rays from something that's on axis because we're pointing our telescope directly at it. And then we've got a bunch of rays from something else, which is off axis. And I will again draw my rays like this. So what we do is we put, now in reality, they usually use mirrors, but the first telescopes were done with lenses. And a lot of the diagrams are a little bit easier to do for lenses, at least initially. So I made these rays go way too far off axis. I was trying to illustrate the wrong point. Usually I exaggerate angles to make a point, but what I really should have done let's make these rays much more off axis. Sorry, much closer to each other, much less off axis. All right, so these things, because they're making such close angles with each other, looking up at them in the sky, they would seem like they're almost at the same point. Well, what would happen is that the first star would form its image, say, here. All of those rays would come together there. And the second star would form its image above that. Now, these two things are still pretty close together on axis. But then what happens is that these rays come in, they hit the other thing, and now I can exaggerate the angle without too much worry because the basic point is made. Whereas the on-axis object still just forms on-axis rays. And so what you do with the telescope is you make these rays form very, very divergent paths. Now you can clearly see one from the other, right? That's what a lens telescope does. Any questions on that? There are two big differences in modern astronomical telescopes. One is that they use mirrors rather than lenses. Anybody care to guess why they use mirrors?
For the reflectiveness?
They are reflective. Why is reflection better than refraction for this?
Because you can redirect light without losing its intensity.
Good glass isn't going to absorb much. Think about the last thing on the assignment I just graded, the one that you turned in on Tuesday. I asked you what happens to the focal length when you change from one wavelength to another. when
Oh,
using
how the
lens.
refractive.
The refractive index changes when you go from one wavelength to another. And so
Right.
everything that we did here is contingent on the separation between the lenses being exactly the sum of the focal lengths. And that is okay if you're just working with one wavelength or two similar wavelengths. But if you are working with a wide range of wavelengths, it's harder to achieve that. Now, what people do in practice is that they use different combinations of glasses so that problems from one lens basically cancel out problems from another lens. But with reflectors, you don't have to worry about that because reflection is reflection, regardless of wavelength. The other difference is that instead of focusing the rays at infinity again, what they do is they focus them onto a camera. So that changes the separations and focal lengths a little bit, but the same ideas still apply. Questions? So this is called an afocal system. And by the way, you don't only use it for telescopes. I mean, that's one obvious thing, but the beam splitter, sorry, the beam collimator that we were talking about a few weeks ago, not even a few weeks ago, was basically the same idea. Remember that situation where we, so I just wanted a line, well, this will do. Okay. We had a lens over here, and then we had another lens that was a diverging lens. And what it did with parallel rays was it spread them out. Going to so this is a beam expander. And the idea was that they look like they're coming from over here. So this would be FB, and this would be minus FA, and this distance would be D equals F, put it somewhere else. This distance would be D equals FB plus FA, and remember that FA is negative. Any questions? Let's play with some of this in Zemax. I posted a Zemax file with two plano convex lenses in it. So go ahead and open that if you haven't already. I'll give you a minute to download that from Blackboard.
Dr. Smollett, the file should be under the files used during class, right? For the 11th.
Yeah,
Okay. I can't. For me, it
maybe it's
doesn't.
on the 9th. It might be
Oh.
on the 9th.
Yeah, it's the same
Whatever.
file.
Yeah, because we didn't get as far as I thought we would on
Okay.
Tuesday.
Thank you.
You're welcome. Give you another minute to download that. Okay. Anybody need more time? Hearing no objection. If we wanted to figure out the focal length, what would be the easiest way to do that? Figure out the focal length of a combo. What was the assumption we used to derive that formula for the effective focal length?
The two focal lengths of each lens.
The focal length of the combination. I wrote down that formula for the effective focal length of the combination. Remember, I wrote down last time, and what was and I reviewed again like 45 minutes ago, the logic that led to that formula. What happens if you send parallel rays of light, rays from infinity, through a lens system? What kind of, where does that image form?
At the effective focal plane, right?
In the focal plane, and how far off axis does it form?
Y tangent. No.
Y tangent? Y tangent?
Yeah. No, Y over tangent.
Y over tangent? Maybe
Y
look in the
equals F
notes.
effective tangent of the tangent.
Thank you, thank you. All right, so let's put our source infinitely far away. So what I always do is for our object at infinity, and it doesn't like something with the object height. It's saying that, you know, if it puts something at a finite distance off axis, infinitely far away, that doesn't really make much sense. And, you know, we'll put some space here. And now what we've got is we've got that the rays of light are coming from infinity, but we see the last few centimeters of their trip.
Can you tile the layout?
Yeah, I'll do that. Let's tile the windows. Window options, tile all windows. Okay. And let's do a quick focus. And then let's look at our fields. We've got, I always prefer to have field 1 be at 0. And yeah, field 1 is at 0. Field 2 is 1/4 of a degree. We're not going to see any, whoa. We're not going to see anything there. So let's put that 10 degrees off axis and let's get rid of that thing. And now how are we going to figure out the focal length of this system? Walk me through it. Because it's what you have to do by Tuesday. Well, again, what's the relationship between how are focal length, angle, and object off-axis position related?
Y equals F effective times tangent of theta.
So I would just say, okay, we've got these rays coming in at an angle of 10 degrees. And I would figure out what this Y is, and it looks like that vertical coordinate is 0.944, give or take, and 0.95, whatever. I'd accept any of those. And, or we could look at our spot diagram, and it says that the image forms at 0.944 centimeters off axis. There you go. So now I know that 0.944 centimeters equals F times tan of 10 degrees. Now, I've been saying that we could turn this around. Let's turn this around. And there are buttons in Zemax that we could click to turn things around, but I think it's better as a human being to figure things out. So we're going to first delete that surface, and then we're going to make this distance finite. And it's not showing the object surface anymore. So what do we have to do?
Change the settings and layout. Sure.
Yep. Okay, now I want these things to form an image at infinity, which means that I want them to go parallel to each other. And the rays are gonna go, or I want to look at what happens very, very far away. So instead of looking and seeing, how many centimeters off axis does this ray go, how many centimeters off axis does that ray go, and so forth, I want to ask how many degrees off axis does each ray go. So I'm no longer trying to focus everything to a point. So we're going to have what we call an afocal image space. Okay, and what that means is that we are now trying to, now we're just trying to see what is the angular distribution. Are these rays parallel to each other? Don't overthink it.
Oh,
No.
No, definitely not. Is the object more than one focal length away or less than one focal length away? Well, are the rays converging? Like they're going to eventually, if we moved this far enough away, looks to me like they eventually come.
Less.
It's less than a focal length away? The object is less than a focal length from the lens?
I'm
The
sorry. Oh, today's just not the day for me.
okay, so if the object is more than one focal length away, we can form a real image. And this thing does form a real image. Quick focus to see where it forms. Looks like it forms a real image there. Okay, it forms a real image as long as it's more than a focal length
It's
away.
more, yeah. Oh, well, you said it. Okay.
So we've got to move this object closer. Now we could do it by trial and error. We could just guess, I don't know, I could try 4. 4 looks like it's pretty good. Maybe not exactly, but that definitely looks somewhat parallel. Let's get this closer up just so we can actually see what's going on. 4 was a way better guess than it had any right to be. But we can also tell Zemax to do all of that trial and error for us. We could just do a quick adjust. And, oh, no, it does not. I thought because it has an afocal image space and the spot diagrams are afocal, I thought it was going to let me take a shortcut that it won't let me take. So if you're confused by what I just did, don't worry, so was I. Let's do this the right way. We're going to send this object, this image, infinitely far away. So we have to insert a surface. I always put this finite layer there just so we can visualize it. And then sometimes Zemax tries to draw anyway when it's at infinity. Sometimes it does, sometimes it doesn't. We're just going to visualize this part of the path. And then we're going to tell it to adjust this thickness. We're going to select that thickness and then go to quick adjust. And we're going to tell it to play with that. And it says 3.987. Now, if we did this correctly, well, we'll get to that for a moment. Any questions on what I did so far? I have my image forming at infinity. And when I select a focal image space, the spot diagram, instead of showing me how many centimeters or whatever off axis each ray is, it shows me how many milliradians off axis each degree is. If you look here at the bottom of the spot diagram, it says units are MR. That means milliradians. And so it's telling me how many degrees off axis each ray goes. Now, remember when, and actually we could change the units. Source, afocal mode units, milliradians. We could go with degrees if you want. Now the units are degrees. You can do radians, milliradians, whatever. Okay. Before we had that when the object was when the object was at infinity on the left and it was 10 degrees off axis, the image formed 0.994 or 944, excuse me, 0.944 off axis. Let's move our object so that's 0.944 off axis. So what I'm going to do is I'm going to take field 2 and I'm going to say, I want this object to be 0.944. And the image forms differently. This system is not symmetric. In retrospect, should that be a surprise?
No?
No, but I'm confused. It's saying that it's 0.17 degrees. I don't quite buy that. It's telling me, and I'm trying to figure out why it's telling me 0.17 degrees. But when I look at these rays look like they're making an angle way bigger than 0.17 degrees. I mean, let's just measure some things. I'm going to go to annotate mode. All right, so I'm going to go to text. Let's see here. In Zemax, I'm in annotate mode, so that's not going to work. Okay. If I make this surface, I'm going to make that surface my reference. And the reason I'm going to make that surface my reference is because it makes it much easier to do coordinates. All right. And so this ray goes, here's horizontal 0, here's horizontal -5. So my horizontal change is -5, and my vertical is from -1.19 to -1.9. So about -1.2 to -1.9, so about 0.7/5. All right, then I go to my calculator and I say 0.7 divided by 5, and then I take the arctangent of that. And of course, it doesn't have arctangents on there. So I go to Mathematica, which does have arctangents. And where did I put my math? There's my Mathematica.
It's about 8 degrees.
About 8 degrees. And we measured all of this rather roughly anyway. So if we're off by a few degrees in some rather crude measurements, I mean, we could, let's test it a little bit carefully. It's worth spending some time on a careful test. So this y coordinate down here is -1.947. And this y coordinate up here is 1.12. 1.947 minus 1.12 divided by 5. Arctan of 0.1654 times 180/pi. So that was in radians. Okay, much closer. I'm happy. I'm not going to try to squeeze out those last decimal places. Besides, it's probably not perfectly reversible because the system is not symmetric, right? Flat on the left, curved on the right. But why is this image 0.17? You know what? We're going to worry about that. Let's try something else. Let's do a full field spot diagram. Here's what a full field spot diagram is. A full field spot diagram takes each of those spots. Right now, these two spots are shown isolated from each other, and it displays them together on the same scale. All right, here the units are degrees, and here it's saying -9 point something degrees. And now I feel better. Any questions? Let's do one last thing before we take a break. Let's see what happens to both of these images if we double the aperture size. If we double the aperture size, sure enough, the spots get larger. That means that the deviation from ideal performance gets worse if you make your aperture wider. What's interesting is that the deviations from ideal performance are very noticeable in the spot size, in the spot shape. I mean, look at this spot. This is very asymmetric. They're not nearly as noticeable in the S1 and S2 values. The thin lens equation is actually a pretty good approximation. And when it deviates from that approximation, when you get a slope that isn't -1, and all of the times I've tried this and all of the times I've read students' reports, there's never much rhyme or reason to it. The discrepancies are quite small. The thin lens equation is almost unreasonably good. Any questions on anything? All right, so at this point, I've given you a file that has 2 thin lenses in it. That might be useful for the telescope part of next Tuesday's assignment. And in previous classes, we talked about how to put the object at infinity. Today, we talked about how to put the image at infinity. So you have everything that you need to do the assignment for next Tuesday and see what happens to the output angle whenever you change the input angle, meaning whenever you change the off-axis angular position of the object. Any questions? All right, how about this? Let's take a 10-minute break. Use some of that 10 minutes to read through next Tuesday's assignment. When we come back, I will ask you if you have any questions on next Tuesday's assignment. We'll go over whatever questions you have. And then I'm going to switch to starting to talk about how we quantify the amount of light collected. So see you in 10 minutes. Okay, let's resume. Any questions on the project due on Tuesday? Anyone? Going once, going twice, 3 times. All right, then I am closing Zemax. And now what I want to talk about for the rest of today and much of Tuesday is how do we quantify the amount of light that we are collecting? Because so far we've just been talking about predicting where an image forms and seeing in Zemax whether it forms sharply or not. But now I want to talk about what happens when we actually try to figure out, okay, well, how many rays of light did we detect? And so I want to start off by defining terms. First of all, intensity, energy per area per time, or power per area. So the units are going to be watts per square meter. And we can often talk about point sources, even though most real objects aren't points. They're made out of points. They're a combination of points. And so if we've got a point source emitting a power P, right? Well, the point source, all of the energy from it is spreading out in all directions, which means that the energy is spreading out over concentric circles that are wider and wider. And the energy on each, the power going through each circle had better be the same. The intensity will be different because as we look, it's spreading out over larger and larger areas. Something spreads over larger areas, same power, larger area. Intensity is power over area. So the intensity has to decrease. If it's spreading over a surface of radius r, that's going to be P over 4 pi r squared. As we go farther and farther away, the intensity gets smaller and smaller, and it decreases as 1 over r squared, meaning inversely proportional to r squared. Any questions so far? So if we're given I and A, we can find the power. If I were told that we've got a source and everything from that source is spreading out in all directions, and we're just going to look at a little surface far away, well, we technically, of course, the intensity is different on different segments. The distance from the source to this edge of it is not exactly the same as the distance from the source to this other point, but we can neglect that for a really small area. And so the power absorbed, if it was just facing it directly, would be I times A. Now, what I asked you to look at on today's homework is what happens if we've got intensity, we've got light hitting a surface that's tilted. So all of our light rays are going like this. but our surface is tilted, right? It's got some area A, but it is tilted at an angle theta. What did you get on the assignment? What did you get for your answer for how much power, the rate at which it would absorb power? It's got to be proportional to the intensity. I mean, if I turn up the intensity and I leave the surface right there and I leave it in the same orientation, I don't change anything. If all I do is turn up the intensity, then the power had better change proportionally. And it better be proportional to the area, because if I doubled the size of it, then I'll get to what's in the chat in a second. If I doubled the size of it, then of course, I'm going to double the power absorbed. But how it's tilted also matters. What you should have gotten is that it's IA cosine theta. And the reason is that the amount of light it actually blocks depends on the width in the direction perpendicular to the rays and the height. If I have something, if I have, say, an entire sheet of paper, right now, the sheet of paper is, I mean, it's reflecting light, so you're seeing it, but it's also blocking light from my face. It's blocking a lot of light from my face because it's covering my face. If I tilt this sheet of paper, it is still blocking light from my face, okay? It is still receiving light from my face, and it is blocking some of that light. And the area of the paper is exactly the same, but it is not blocking as much light from my face because of the way it is tilted with respect to my face and the camera. Think about a solar panel, all right? Intuitively, you know that you want to point that solar panel at the sun. That's why solar panels are usually on, well, sometimes solar panels are just fixed to the roof of a building, but sometimes you'll see these collections of solar panels on things that can move. And even if they're not on things that they can move, they're tilted so that they'll at least be pointed more or less in the direction of the sun for a lot of the day, even if not all of the day. Intuitively, you know you want to point it at the sun. If we had it tilted so that the sun was just looking at the edge of it, intuitively we know that that couldn't possibly work. That's the idea here, okay? What matters is how the area is tilted with respect to the beams of light. If they're hitting it head on, then they see the full area, all right? So if I've got a situation with a whole bunch of, I'm just going to first draw a whole lot of rays. Intuitively, we know that if we've got it, say, like this, I'm not going to try to, I'll try to do an effect like that. Intuitively, we know that if we've got it so that the full height of it is presented to the rays. Well, that. All right, it's head on. But if I took the same thing and I tilted it so it's just as wide, presenting just as much width, but less height, well, now this, I'll call this L to stay consistent with the homework, IWL. Well, now we've got this distance is L. This height here is L cosine theta. So now we're just going to absorb I times W times L cosine theta. So this is IA. This is IA cosine theta. You might say, why is there no cosine theta in the top case? Well, what's the angle in the top case? What's the angle between the normal to the surface and the rays in the top case.
0.
Yep. And cosine of 0, last I checked, is 1. Here now there's a larger angle between the normal to the surface and the rays. Okay, so it's I times A times cosine theta, where this is the angle between surface and rays. And that determines how much is actually absorbed. Any questions so far? All right, let's do a situation that involves a point source and a surface, and we're only going to look at a certain circle in that surface. Just look at a circular region of radius r. And this distance will be L, and we've got a point source here. Power absorbed is what we want to calculate. Well, is the intensity the same at every point in this circle? Yes or no? Is the intensity the same everywhere? My point source is right here.
No.
No.
No. So if the intensity is not the same, that doesn't mean we can't just multiply I by, I don't know, pi r squared. I mean, pi r squared is indeed an area. It's the area of the thing, but I is not constant. For that matter, is cosine theta the same everywhere? Definitely not. The direction out of the surface is the same. It's always to the left, but here's theta, and here is r, the distance in polar coordinates. We're going to have to work in polar coordinates. So let's see here. Cosine theta would be, well, here's theta. This is the angle between the direction of the ray and the direction of the ray and the thing perpendicular to the surface. You tell me, what's cosine theta when we set up this problem? I'm a distance r from the center, and the point source is a distance L from the surface.
You're asking for cosine theta?
Yep.
Then it would be L over the square root of r squared plus L squared.
Yep. Because this distance, the distance from the source to the surface, is square root of r squared plus L squared. All right, so that's cosine theta. The intensity is going to be P over 4 pi times that squared distance, which is L squared plus R squared. And we have to integrate that over every single point in the surface. So we can break up the surface into little elements, except that we could work in Cartesian coordinates. All right, we certainly could do that. why would we not maybe want to work in Cartesian coordinates?
It's a lot of trig.
It's a lot of trig. I mean, we're going to be doing some trig no matter what we do. We already had to use the Pythagorean theorem to find that distance and to find some cosine theta. But our limits of integration, all right? I mean, here, x equals r. Well, that's nice. And here, y equals big R. That's nice. But over here, x squared plus y squared is equal to big R squared. So here, x is the square root of big R squared minus y squared. Doing integrals with limits like that is never fun. Usually when you do integrals with limits like that, you wind up doing some trig substitutions, and those trig substitutions become equivalent to doing a change of coordinates to polar coordinates, which is what we should just use in the first place, all right? So if we work in polar coordinates, then we've got this distance r, we've got a little shell. And dA is 2 pi r, the circumference, multiplied by the thickness dr, 2 pi r dr. So when we put all of that together, P is the integral of I cosine theta dA. We're integrating from r equals 0 to big R. I is the power over 4 pi times L squared plus R squared. Cosine theta is L over L squared plus little r squared to the, oops, to the 1/2. I'm skipping a step on myself. I'm skipping ahead, which I shouldn't do. I was anticipating an upcoming result. And then our dA was the circumference of that ring multiplied by dr. So that's a 2 pi r dr. Somebody must have a question on one or more of these factors. Okay, we'll just go ahead then. All right, so first we cancel whatever we can. We pull out constants. So LP over 2, integral from little r equals 0 to big R of r dr over, this is L squared plus R squared to the power 1. This is L squared plus R squared to the power 1/2. So we add up those powers and we're left with L squared plus R squared to the 3/2. I think at this point, it would make the most sense to do a U substitution. To say U is L squared plus R squared. So du is 2r dr, or r dr equals du over 2. So that becomes LP over 4 to grow from, technically I should change my U, change these variables of integration to U, but we'll just substitute back in at the end. Okay. So we need something whose derivative is u to the minus 3/2. That would be LP over 4. Whenever we integrate a power, we add 1 to the power. And so we're going to have u to the minus 1/2 evaluated from r equals 0 to big R. But we also need to multiply by -2. Because when we take the derivative of u to the minus 1/2, we need a -2 to cancel it out. So we just, to cancel out the minus 1/2. So we just get u to the minus 3/2. Or minus LP over 2 times 1 over the square root of 1 over the square root of u, which is 1 over the square root of L squared plus little r squared, evaluated from 0 to big R. Any questions at all?
I have a question. Why did the limits of integration not change when we did the U substitution?
Because I was sloppy, because they really should have, but I always
Oh, okay.
intended to change back to R at the end. If I had done this more carefully, then I would have said that u is L squared here and u is L squared plus R squared there.
Okay, thank you.
And using u as a singular third person subject means I'm always saying you is, and I always feel like I'm some guy from a gangster movie. Hey, you's got a problem? Hey, what's the, I think you is asking too many questions. I like accents. Anyway, so when we put all this together, minus LP over 2 times 1 over square root L squared plus R squared minus 1 over square root of L squared. Well, let's see here. Square root of L squared is just L. And the minus sign, I can multiply that in and flip things around. So I get P over 2 times L over L minus L over L squared, sorry, square root of L squared plus R squared. Or P over 2 times 1 minus L over square root L squared plus R squared. Any questions? Okay, well, let's look carefully at this L over square root of L squared plus R squared. If we go back to our diagram, what would that be? I mean, there's no, you can't just point at the diagram and say, oh, it's this symbol, because there is no symbol for that. But just qualitatively looking at it, what would that seem to represent?
Oh, sorry, which part of the expression?
L over square root of L squared plus R squared. On this diagram, do we have anything that's L over the square root of a radial distance squared plus L squared?
Well, we're not mathematically, right? You mean if there's like a different insight we can provide besides relating it to cosine?
It is a cosine. It's the cosine of a very particular angle, the angle at the edge.
Oh, yes.
All right, and this angle at the edge has a special name, so I'm going to redo the diagram because that diagram was getting kind of crowded. This is called alpha. This is the acceptance angle. This is the range of angles that you can accept. All right. So if I'm only looking at, say, a circular opening or a circular detector or whatever, alpha is the acceptance angle. It's the largest off-axis angle that passes through our surface. Acceptance angles show up a lot. I mean, if I had a lens, optic axis, say I put my object here, do not assume that it's a focal length away. Might be a focal length away, might not. But I've set up my lens to collect light from something at this distance, whatever that distance may be. Then sine alpha would be equal to, if this is S1, and this is the outer radius of the lens, sine alpha would be R over the square root of R squared plus S1 squared. Fiber optic cables have acceptance angles. Often it has less to do with the dimensions of it than with the fact that light is only accepted. Like you don't have to just talk about point sources. It wouldn't matter where the light is coming from. Only within a certain range of angles will it successfully confine the light. So fiber optic cables will have acceptance angles. Here, what we've got is we've got P over 2 times 1 minus cosine of alpha. Any questions on the concept of an acceptance angle? In Zemax, you could think of it as the maximum angle that a ray could come in at and still get all the way through the system. If I've got several lenses in a row, then a ray might make it past the first lens, but then get bent at some really extreme angle and not make it into the second lens. So whatever that limiting thing is, you just have to ask, what's the maximum angle at which something can come in and still get through all of the subsequent elements of the system? Let's see, 1 minus cosine of an angle over 2. What does that look like from trig?
Sorry, so does this apply to a system of many lenses when talking about an acceptance angle?
I'm just saying that we've got a range. An acceptance angle is the maximum angle that can get through the system. A lens, a fiber, or whatever.
Okay.
And I'm saying
I guess
that,
it just kind of like, it confuses me that like it doesn't take into consideration any other range of angles required for the sizes of other lenses, or I get that doesn't
It
seem
could be.
obvious to me, that claim at least.
So all I said was that we've got some surface here. For all I know, maybe we've got a really elaborate system of lenses, and I'm going to get details wrong if I try to come up with off the top of my head, but it doesn't matter. Who knows? Maybe for whatever reason, a ray coming out at this angle could enter the system and do whatever it does, but then it would just get sent way down there and never make it into the last lens.
Right.
But this ray will do whatever it does and make it through the last lens. All right, this would be our acceptance angle. And wouldn't it all be obvious that that's the acceptance angle? Okay, it's not like you could just look at it and say that's the acceptance angle, but that's, somebody would have to do some experiments and conclude this is the angle we care about. This is the maximum angle that we're going to worry about. And these other rays are going to get through and they're going to do whatever and then finally leave. Okay, fine. We're never going to model these larger angles. They're irrelevant to us. It would be just the same as if somebody said, well, you know what then? I'm just going to black out this part of it. Okay, I'm just going to put some spray paint on there. It wouldn't matter. All that matters is that we're talking about this, somebody has worked out through calculations, through simulations, through experiments, through whatever, that this is the range of angles that can get through the system. Okay.
Gotcha.
And if I put a source here that's emitting power at a rate P, I could figure out how much power actually gets through the system. And that power would be equal to power that gets through would be P times 1 minus cosine alpha over 2. Or maybe it's not a lens system. Maybe we've got a surface and over here it's coated with light absorbing material. And out here, it's just got other stuff. I mean, real semiconductor detectors are, printed onto surfaces that have lots of other things going on. There are parts of the surface that have some sort of photosensitive material, and there are parts that have wiring in order to carry out all of the functions needed to convert into a signal. But we don't really care right now. All we care about is that there's a range of angles, and if it hits the surface within that range of angles, it will go through a lens, it'll go through a detector, it'll go through a whatever it is that light needs to enter to do the thing that we need to do. All right, it's a very general concept. Questions so far? Well, let me just note, what does 1 minus cosine alpha over 2 look like from trig?
The
Sine
double
squared.
angle formula?
Not a double angle formula, but you're on the right track.
it
There
the
is a
half angle?
factor of 2. What?
Half angle?
There is a half angle in there. You're on the right track. Because sine squared theta is 1 minus cosine of 2 theta over 2. All right. So if I replace theta with alpha over 2, I get 1 minus cosine of 2 times alpha over 2, whole thing divided by 2, and the 2 alpha over 2 is just alpha. Here's an interesting thing about this point source. We started off with a geometry that had a bunch of lengths and radii on it. Okay, we had a point source that was whatever distance away from our surface, which might be the front surface of a lens, it might be a semiconductor detector, it might be a fiber optic cable opening, it might be whatever. We start off with this distance and we start off with a radius and said we're only going to worry about rays that enter anywhere between the center and a distance big R away from the center. And we wind up with a result that only depends on the acceptance angle. Okay? The fraction of light collected from a point source only depends on alpha. Let's check this. Intuitively, if I had a detector that went way up there so that even light coming out at like almost 90 degrees was detected, or better yet, much more realistically, I had a hemispherical surface. I never said anything about the surface being flat, okay? Maybe I have a hemisphere, and I know people who have designed hemispherical surfaces, or even more than hemispherical surfaces, to collect as much light as possible in an experiment. In that case, what is alpha? Don't overthink it, just look at the diagram.
90 degrees.
Okay, so sine squared alpha over 2 is sine squared 45 degrees, which is 1 over the square root of 2 squared, which is 1/2. So we collect exactly 1/2 of the light. And if somebody built a spherical detector, and such things exist, they're called integrating spheres because they add up over all possible angles. Alpha is, well, some would say 360, but the whole idea is that you could go out this far or that far. So alpha is 180 degrees. Sine squared alpha over 2 is sine squared 90 degrees, which is 1. So the formula works. Next time, what we're going to do is we're going to talk about a couple of other ways that people measure the amount of light that a source can collect. And then we're going to talk about the question of whether pixel size matters, which turns out to be way more subtle than you might think. And we'll end a couple of minutes early. If anybody has to talk to me about something, feel free to stay after. Otherwise, have a good weekend.
Have a good one, Professor.
Have a
Thank
good
you.
one, Professor.
Thank you, you too.